Well, delta H reaction, the heat of reaction, can be calculated using standard enthalpies of formation. In lab, well, they've moved back there now, but in lab we've referenced the CRC to look up some densities. That also has very extensive tables of different values in it, like delta H. And so they've tabulated what are called the heats of formation. It's not practical, or maybe not even possible, to list delta H for all possible reactions. So they've come up with an easier way where we can calculate the delta H for any reaction that we want from that table. And we do it in this way. Delta H is a state function. It's the change in enthalpy. And enthalpy is relative, and so we can define 0 to be whatever we want, something convenient. Just like elevation. We measure changes in elevation relative to sea level. Why? Because it's easy. Okay? Most countries have a coast, right? If there's a coast, there's the ocean, that's sea level. Not super precise because the tide goes up and down, right? But it doesn't go up and down that far if you're trying to measure mountains, right? So it's convenient. We measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. So we just decided that this would be the most convenient thing to do. We're going to measure enthalpy changes relative to elements in their standard states. So what are standard states? It's a specifically defined set of conditions. If the element in question is a gas, the standard state is the pure gas at exactly 1 atmosphere of pressure. If it's a liquid or a solid, it's the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest, usually 25 degrees Celsius. But you can find tables that will give these heats of formation or standards for other temperatures as well. For a substance in solution, it's a concentration of 1 molar. So the standard enthalpy change, this is delta H with a degree symbol here, and that means standard. That's the enthalpy change when all the reactants and products are in their standard states. And the standard enthalpy of formation is defined as the enthalpy change of the reaction forming 1 mole of whatever that compound is from its elements. And so then we stick an F subscript on this. So this is the standard heat of formation. The elements are in their standard states. The elements, pure elements in their standard states, all have heats of formation of 0 because that's what we decided was the 0 point. Any questions yet? Here's a small table from chapter 6 showing some enthalpies or heats of formation. If we let's look at carbon. So carbon, solid carbon has 2 common forms, graphite and diamond. Graphite is the more stable form, and so its heat of formation is 0. This is carbon in its standard state as an element. To make carbon diamond, it has a heat of formation of 1.88 kilojoules per mole. So that tells me it's less stable. And so some of the elements, like here's hydrogen atoms and hydrogen molecules. Well, this is hydrogen molecules are the most stable. And so that's where the heat of formation is 0.
What exactly is heat of formation like? How much?
The standard heat of formation is the change in enthalpy for a reaction forming whatever that is from elements in their standard states.
Okay. So that's why H would be 218, because you need energy to go in to break that bond?
Right. If you want to make hydrogen atoms from hydrogen molecules, the enthalpy change is going to be positive. Energy has to go into that to break those bonds. And if you look at this, you'll see a lot of the compounds have negative enthalpies. That means that energy is released when they are formed. So standard enthalpy of formation, also called standard heat of formation. Remember, enthalpy and heat are generally the same number at constant pressure. And so that's why we use those terms somewhat interchangeably. So standard enthalpies of formation for elements are 0 because we defined it that way. That's like being at sea level. Changes are measured relative to that. For most compounds, the heat of formation is negative. So, if you're continuing at the sea level idea, their elevation is negative, it's below sea level. Let's look at the formation of methane. So standard enthalpy of formation for methane. If you take methane, CH4, and form it from its elements in their standard states, that's carbon in its graphite form and hydrogen as a diatomic molecule, the heat of formation is minus 74.6 kilojoules per mole. We always write these formation reactions to form 1 mole of the substance in question. And we're going to learn how to write these reactions. If you're not sure what the standard state is for any given element, look in the table and find the state, the form of it that has delta H 0. When we're writing these formation reactions, we can end up with fractional coefficients because the definition requires that we make 1 mole. So let's look at how to write the equation for the formation of carbon monoxide. So carbon monoxide, what are the 2 elements involved? Carbon and oxygen. So then we have to identify what's the standard state of carbon, what's the standard state of oxygen. So for carbon, it's graphite, and for oxygen, it's O2. So we can go back to that table. Yes?
Are all the diatomic forces?
Yes, all the diatomic elements, their standard state will be diatomic molecules. So here for oxygen, we see that the standard state is the diatomic molecule. And some of the other ones are in here. There's hydrogen, there's fluorine, there's chlorine, nitrogen, bromine. So all the 7 diatomic elements, their most stable form is going to be the diatomic molecule.
So that doesn't mean that no heat was released when those were made. It just means that that's our reference point.
That's our reference point. That's our reference point because if you have pure hydrogen, the most stable form of it, meaning it's going to have the lowest enthalpy, is going to be the diatomic molecule.
Okay, gotcha. Just want to be sure.
Yeah, it's good to ask questions. So then we come up with these for the formulas of the elements. Now, is this a balanced chemical equation? No. We have to have 1 as the coefficient of our product. So how could we fix this to balance it then?
Break the bond, switch it to O2, and have the negative. Or the positive.
Well, all we can do is put coefficients.
Oh, 1/2.
1/2, yeah. So we're going to put a coefficient of 1/2 in front of the oxygen. So when we do that, now 1/2 O2, that's 1 oxygen atom and 1 carbon atom. And then over here we've got 1 carbon and 1 oxygen. And we can look up the heat of formation in the table. The heats of formation for many of these compounds are in that table or in the table in the back of your book. Yes?
So is the heat of formation just going to be what it takes to break that oxygen bond?
Is the heat of formation going to be what it takes to break the oxygen bond? Well, there's a bond being broken here, but there's also a bond being formed. And so this is the difference in energy between breaking and making. Yeah. So when carbon monoxide is formed, the enthalpy change is minus 110. If we take carbon monoxide and we want to break it into its individual elements, that will require that we put in 110 kilojoules of energy. So let's do a couple of examples. Write equations for the formation of sodium chloride and lead 2 nitrate from the elements in their standard states. Include the values of the heat of formation for each equation. Well, let's do the first one first. So A, here's our product. This is what we're trying to make. So I'm going to write that over here. NaCl, solid. It's got 2 elements in it, right? Sodium and chlorine. So those are our reactants. Sodium and chlorine. Well, let's think about it a minute before we go look at the table. Chlorine is a diatomic element, right? So we're going to guess that the most stable form, the standard state, is going to be Cl2. And at room temperature, what is the physical state of chlorine? It's a gas. So sodium, is sodium a diatomic element? No. It's a metal, right? What is its physical state at room temperature? Solid. So those are our guesses, okay? Let's go back and look at the table. Here, sodium. There's sodium solid and sodium gas, but the one with the 0 is the solid. That's the most stable form of sodium at room temperature. We go over here and look at chlorine. There's chlorine atoms and chlorine molecules. It's the chlorine diatomic molecules that are the standard state. And while we're here, let's look up the heat of formation for sodium chloride because we're going to need to write that down. Minus 411.2. The units are kilojoules per mole. Oops. So, delta H formation minus 411.2 kilojoules. Okay, so we've got our standard states here. Is this balanced? No. Normally we would balance this by putting a 2 in front of sodium and a 2 in front of sodium chloride. But we need the product to have a coefficient of 1. And so we're going to put 1/2 as the coefficient for chlorine. Still balanced, it's just not the regular way. Any questions? Okay, let's do the second one. So B. Here our product is lead 2 nitrate. PbNO3, 2. And it says that it's solid. Well, we got 3 elements here now, right? Lead, nitrogen, and oxygen. We're not forming this from the 2 ions, the lead ion and the nitrate ion. We're forming it from the elements. So we have to list all the elements separately. So lead, what's probably its standard state? Solid. It's a metal. And we've got nitrogen. Is nitrogen a diatomic element? Yeah. And it's a gas at room temperature. So it's probably going to be N2 gas. And then we've got oxygen. That's a mess. Sorry. So if we go looking in the table of heats of formation, we find that these are indeed the standard states for those elements. And we can look up the heat of formation for this compound, delta HF, is minus 451.9 kilojoules. And then we need to balance the equation. And we need to do so without changing the coefficient on the product. So 1 lead and 1 lead, that's fine. How many nitrogen atoms are in the product? 2. Oh, and there's 2 in the reactant, so that's cool. How many oxygen atoms? 6, and here we have 2. So this time we didn't need a fraction, but we just stick a 3 there. Any questions?
And the specific heat for the PbNO3 2 is I mean, not the specific heat.
The-
delta change, formation,
the-
enthalpy, whatever.
Standard heat of formation.
Standard heat versus, yeah, that one.
I looked at
451.9, and that's everything combined, of course, like all the reactions.
Yeah, so this is the heat of reaction for forming lead nitrate from its elements. Now, is this a common way to make lead nitrate? No. A lot of compounds are not made from their elements. But what we'll see is that we can use these equations and Hess's law and add them together and figure out what the heat of formation is from the reaction that we're actually using. Okay, so this is really just a step in the process.
So we could break all this down and figure out the specific heat, and that will add up to that.
Yeah, so what's important to realize about this is the heat of formation for lead nitrate, but if we took lead nitrate and we're going to take it apart into its elements, then all we have to do is change the sign on the heat of formation. So let's look at that. So those were heats of formation. Now what about calculating a standard heat of reaction, where something's being formed but not from its elements? That's more useful. So this is kind of what I just said. So we looked at elements going to the compound, that's the heat of formation. We can look that up in the table. But then let's remember that we can take that compound and break it into its elements, just reverse the equation and reverse the sign on the heat of formation. So what we're doing when we're calculating these standard heats of reaction is that we are, in our minds, decomposing the reactants into their elements in their standard states and then forming the products from their elements. We don't actually do that, but if we think of it that way, then we can just add stuff together because enthalpy is a state function. It doesn't matter how you got there. Whether you broke them down into elements and reformed from elements, or if you just went straight from the reactants to the products, the enthalpy change is the same. And so it's easier mentally to do it into the elements and then bring them back together. So any reaction can be written as the sum of the formation reactions or the reverse of the formation reactions for the reactants and products. And when we do this, the heat of reaction is going to be the sum of the heat of formation values for all of those reactions that were involved. Hopefully this will become a little more clear when we do the example. So mathematically we can state it this way, which you may or may not like. Standard heat of reaction equals the sum of the molar amount, the coefficient of that substance, times its, oh man, I didn't even notice this, just those are supposed to be F's. Wow, that's an F. That's bad.
Yeah, that makes more sense.
Yes, there we go. It's the coefficient times the heat of formation for the product, and if there's more than one product, it's the coefficient times the heat of formation for the other product. You add them all up together. That's the sum of those. It's products minus reactants. And then you subtract the coefficient times the heat of formation for the reactants, and you add all those up together. So let's look at this example. Doesn't that look like a mess? Okay, so at the top here, this is the reaction that we're interested in, the combustion of methane, and we want to find the standard heat of reaction for this. So what we're going to do here is we're going to mentally break methane into its elements. We looked at that reaction before, the formation of methane. If we break it into its component elements in their standard states, graphite and hydrogen, this is the heat of formation with the sign changed. Because we're not forming the methane, we're taking it apart. So we can take that apart. Now we have elements in their standard states. And so we can look at the formation of carbon dioxide from elements, oxygen and carbon. And you can look that heat of formation up in the table. And then we're going to look at the heat of formation for water. And it's 2 waters, right? We're making 2 of them. So we take the heat of formation of water multiplied by 2. So that's this one right here. These are the individual formation reactions in the table. So carbon plus hydrogen to make methane. There's the heat of formation. So here what we're doing is we're doing the reverse. We're taking it apart. It's like you're taking your Lego structure and you're taking it apart into all of its individual blocks, and then you're building the new thing. Putting carbon and oxygen together to form carbon dioxide, there's the heat of formation. That's this guy right here. And putting hydrogen and oxygen together gives off 241. But we're making 2 of them, so then that gets doubled. So we had to invest energy taking apart the methane, but then more energy gets released when we form the carbon dioxide and when we form the water. And so the overall change is from here to here, even though in our minds we went up and over this mountain to get there. The overall change is adding these terms up. And so we get minus 802.5. That make any sense?
I thought we just said that we take a compound and get down to the elements.
When you take a compound, when you form a compound, often the heat of formation is negative. When you do the reverse, when you take a compound and break it into its elements, the delta H is going to be positive. Well, it's either cold or you had to do something to it. Y'all seem a little dazed.
I think what you were saying, which I agree with, was like, you said that when we go one way or another, the sign just changes.
Yes. So here we have, where is it? This one. This is the formation reaction for methane. The heat of formation for methane is minus 74. What we're doing here is we're going methane to carbon and hydrogen. We're doing the opposite of this equation. And so we change the sign from negative to positive.
And then you're just going a step further too, and that's why it keeps going, right?
Yeah, and so now we've got these elements, and now we're looking at putting them together. Well, the formation of CO2, that's formation. That's in the forward direction. We keep the sign that was on delta H. And this going, the combining of hydrogen and oxygen going forward, that's the same forward direction, but we multiplied this reaction by 2, and we multiplied this one by 2. Any other questions? So let's do an example. Let's see if I can do what I was trying to do earlier. So here is the appendix, the table that's in the appendix of your book, because these heats of formation are not in the table in the PowerPoint. So we've got Fe2O3. I should use this pointer. Here we've got Fe2O3. This first column is heat of formation. Delta G and S, you'll learn about in the second semester. So for Fe2O3, it's minus 824.2. Fe2O3. And the other compound that's in that example is aluminum. I really just need to type those in so I don't have to do stuff like this. So here's aluminum, Al2O3, heat of formation for that minus 675.7. 1675.7. So that's information we have to go look up. You do not memorize a table like this. Students are always asking, do I need to memorize the table? No, do not.
He said yes, I'd quit.
Yeah. I kind of feel like I shouldn't ask students to memorize stuff that I don't remember myself.
That's fair.
Doesn't that seem fair? And I don't require you to memorize everything that I remember, because that wouldn't be fair either. I remember some pretty strange things. Anyway, okay. So we've looked up some stuff. Now we can do this problem. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic. Anybody ever seen this reaction as a demo? Maybe we'll check out a video. I can't do it in a building. It's very exothermic. Use standard enthalpies of formation to find the standard heat of reaction for this reaction. So the idea here is that we're going to mentally take the reactants apart. Well, this is aluminum. This is already the standard state for an element. But here we have iron and oxygen. So mentally taking those apart, that is the opposite of the heat of formation. And then we're going to form this from its elements in the standard states. And this is already an element in its standard state. So the standard enthalpy of formation, the standard enthalpy of reaction for this is going to equal the heats of formation for the products, so delta H F for Al2O3 plus the heat of formation, 2 times the heat of formation. Didn't mean to do that either. 2 times the heat of formation for, I really shouldn't talk while I write, for iron. So we're looking at the 2 products. Those are the things that are being formed, and so their heats of formation are going to retain the original sign. And then we're going to subtract the heats of formation of the reactants. So we've got 2 times the heat of formation for aluminum. And then we've got the heat of formation for Fe2O3. Okay with that?
Give us a second copy, Jen.
And this taking the products and subtracting the reactants, the way I remember that is this is delta, right? Delta is always final minus initial. The products are what you end up with. This is the final part. The initial part is the reactants. So you're taking the products and subtracting the reactant information. So the heats of formation for both of the products, subtracting the sum of the heats of formation for the reactants. Now, some of these heats of formation are 0, aren't they? What's the heat of formation for iron? Well, that's already an element in its standard state. The heat of formation for iron is 0. So that one's 0. And in the reactants, which one of these is 0? The aluminum. This is an element in its standard state. That's also 0. So we don't even have to do those. So we end up here, the heat of formation for aluminum Oxide is minus 1675.7 kilojoules. And then we're subtracting the heat of formation for the iron, which is negative 824.2 kilojoules. Now be careful with your minus signs when you do that on your calculator. Negative 1675.7 minus negative 824.2 minus 851.5 kilojoules. Any questions? It's an exothermic reaction. We came up with a negative delta H, so that's a good sign.
And that's just heat of the reaction.
That's the heat of the reaction.